Here. I hope you can all see my slides. And let me say that it's intentional that the small slides that you see on the side, so that you can always look back if sort of you want to go back at the last slide you saw or something like this. And yeah, as I was saying, thank you so much for having me. I'm very excited to tell you a bit about a project we started with together with Yassine El Mazouz, Marvin Hahn, Gabriele Nebe, and Bernd Sturmfels. And this is sort of the starting point. I want to tell you a bit what the problem is, what the results are, and what also the future goals are of this project. So let me start by telling you what the main idea of today is that we will be looking at a picture like the following. So we'll have a positive integer d and a d by d matrix with integral coefficients. And to a matrix like this, we can associate both an OK module in K to the D times D. I will introduce all this notation in a second. So we will have a module on one side and a polytrope on the other side. And the main thing that we want to do today is understand what the interaction between these two objects is. So keep in mind this picture. And let me tell you that really the pioneers of the study were Plesken and Sassenhaus. But what we did was both to interpret the results in terms of tropical geometry, and also we then expanded what they did. And this is what I want to tell you today. One thing I should say is that here and there I will be referencing to results to Plesken, because these are results that belong to Plesken's book, but then in there he credits Sassenhaus. So this is just for clarity. Okay, very good. So here's the setting. So K will be for us a field with a surjective valuation, and then into the integers together with infinity. This is where we send a 0. And then OK will denote the valuation ring of K, which just consists of all the elements that have non-negative valuation. And this is a local ring with a unique maximal ideal consisting of the element with positive valuation. And it is principal generated by one element that we pick once for all, okay, what we call pi, denoted with pi, which is the uniformizer. And once we have a valuation on K, we can also extend it to any vector space or matrices over K, right? We do just this entry-wise. And here at the bottom of the slide, you can see that I wrote, we will disregard infinity as a valuation in the sequel. But what do I mean by this is that, if you remember, I showed you, we started with the matrix M with integral coefficients, and M will be, you should think of it as a matrix of valuations. So something like this, though M does not allow infinity. So this is just one thing to keep in mind. So this is the last slide in which we see infinity. Very good. So yeah, we go back to our M, and we can define a module from M, which consists of all the matrices with coefficients in K, D times D matrices, whose entries have valuation at least what you see in M. And because of the defining properties of the valuation, this is an OK module. We can even say more about the structure of such a set. It's not only an OK module, it is a free OK submodule of the ring of D by D matrices coefficients in K. And it has rank D squared. So if we tensor up with K, we get the whole thing. And also, by definition, lambda M lives in a ring. So it makes sense to ask, when does this module have the additional structure of a ring? Okay, let's see an example. So here is an example in which I put K to be Q, D is equal to 3, and the valuation is the p-adic valuation. So yeah, for an element in Q, we have numerator, denominator. We just look at the number of times that P divides the numerator, the number of times that P divides the denominator, and then we take the difference of these values, and this is the p-adic valuation of any element. So if we look at the valuation, at the p-adic valuation of the matrix X here, what we get? We get the matrix M with all zeros, entry zeros, except for a 1 that is in the top right corner. However, if we compute X squared, this is the matrix that we get. And you see that according to the prime that we picked to define the valuation, we will have different entries here. However, in the top right corner, we will always have valuation 0 because this entry here, I hope you see my pointer, is 1 modulo P. So you see that the valuation of X squared is not at least the valuation of M. So lambda M is not a ring in this case. Okay. Here's an example in which though lambda M is a ring, so if I just take the matrix of all zeros, then I do get a ring. Which ring is this? Well, it's just the matrices D by D with coefficients in the valuation ring. This ring has even more structure than just being a ring. It is what it's called a maximal order in K to the D times D. So what do I mean? First of all, by an order. Well, to define an order, I first need the notion of a lattice. And a lattice in K to the D is just a free submodule, OK submodule of rank, of full rank. And an order is just a lattice like that that has also the structure of a ring, so multiplicatively closed. And maximal just means that it's not properly contained in another order. And right, we'll see that these objects are actually pretty nice. And rings of the form lambda M are called, well, we decide to call them graduated following Plesken and Sassenhaus. However, there's other names in the literature. So for example, people call them tiled or split or monomial. Okay, so when I say graduated order, I mean a ring that has the form lambda M. Are there questions so far? Guess not. Okay. Then here is a proposition of when we can expect lambda M to be a ring. It's necessary and sufficient that the matrix M has zeros on the diagonal and that the entries satisfy this triangular inequality. So for each index I, j, and k, we have that mij plus mjk is at least mik. And since these matrices are important for us, the ones with zeros on the diagonal, then we just decorate a z d times d with a 0 to indicate the matrices that have the zeros on the diagonal. And I want every time, right, we assume 1 when I want to talk of rings. So when I say lambda M and I imply that it's a ring, keep in mind that it has to satisfy this. Very good. Okay. So what do we do with these rings? Well, since they're subrings of rings of matrices that naturally operate on K to the D. And so what we can ask is, what are the stable lattices in K to the D? So those that are sent to themselves under this action of lambda M. And just for convenience, if I take the standard basis, then the standard lattice in K to the D, I will just denote it by L0. So here are some examples. If I take the matrix with all zeros, then I get OK to the D times D. And if I compute what the stable lattices are, well, I just get the standard lattice and all multiples of it by either, you can write it as either powers of the uniformizer, or you can substitute these by just elements in the field that are not stars. So either they preserve or they go up and down. And in general, if you have a maximal order, as OK to the D times D is, then we know that lambda m will be conjugate to OK to the d times d. So then the collection of stable lattices, they will be of the same form. So, and this is a general thing for maximal orders, that the collection of stable lattices, they are all just represented by 1 and its scalar multiples. One other thing that we can remark immediately, if you think about it, if you take two stable lattices, so it just means they are sent by lambda m, they're sent inside themselves, then if you take their intersection or their sum, they will also be lambda stable. So this means that whenever we have a bunch of stable lattices, we can create more by using these operations. And this is also pretty nice. Okay. So here is the classification of the stable lattices. And I am doing this now in terms of the original language of Pleskin and Sassenhaus, but I promise you later we come back and look at this from the point of view of tropical geometry. So if we start with the graduated order, so once again, a ring that comes from a matrix, and we want to classify all the stable lattices, then these are parameterized by integer vectors that satisfy these inequalities here. And how do these vectors parameterize these lattices? Well, we can define each a lattice LU for each U, starting from the standard basis and then allowing shifts by the uniformizer to the power the entries of the vector. And this is everything we can do. So this inequality describes all the possibilities for the stable lattices. So as you see, this is very combinatorial. And also we even know more. Any two stable lattices will be isomorphic as lambda modules if and only if we can write one as the other up to a scalar multiplication by the uniformizer. So we have complete control on whatever is happening with the module structure in the for the lattices. So here's the definition, then we immediately look at an example. Since you see the fact that we can multiply up and down by the uniformizer is important, and sort of all of these, once we have one, we have all of them for the stable lattices, we will call them equivalent. So we sort of wanna treat them all together as one. And since we said this is all very combinatorial because we can define this from just vectors in Z to the D, we call these lattices LU diagonal because they have a compatible basis. And compatible basis means that we can really define them by just starting from one basis and then doing these shifts. Of course, if you take a lattice in K to the D and apply a transformation, a linear transformation, then you get another lattice. So not all lattices in K to the D have this shape. So these have a special shape and we call them diagonal for this. Okay, let's see one example. So here is a matrix M that defines a ring. So you can check that those triangular inequalities that I gave you at the beginning, they are satisfied. And all of the dots in this figure, they represent equivalence classes of stable lattices. So what do I mean by this? I mean that I can take L defined as, for example, let's look at this one, this entry here. I can take L defined to be P to the 2 E1, first basis vector, P to the 3 E2, and then P to the 0, so just E3. And then, of course, then I can allow shifts as we saw before, but we said we want to treat them all as the same guy. So this is what it means. So if I want to treat all lattices that are equivalent together, it just means that I fix a U and I get all the other u primes as shifts by u of u by n times the all one vector. Okay, and this is what the picture does, because you see I picked here entries that all have the 0 as the last entry, but I could have picked anything else as a representative. All right, and if I have, let me also say that if I have an element u and z to the d, then I can always define a matrix associated to u as by taking just the differences of ui and uj. And this gives me a matrix that has zeros on the diagonal. It also satisfies the conditions for defining a ring. What ring is this? Well, this is the endomorphism ring of the lattice defined by u. So this is just the matrices in k to the d times d that have valuation at least mu. What can I use this for? Well, for each u in my picture, I can define mu. Then I get all these endomorphism rings. If I intersect them, I get the lambda associated to this matrix. So this brings me to the following definition. If we have a collection of lattices in k to the d, then we define the Pleskens-Sassenhaus ring of this collection as just the intersection of the endomorphism rings of these guys. And this will define a ring, a subring of k to the d times d. It does not need to be graduated. It does not need to be of the form lambda m, but sometimes it will. And let me say that here are some remarks that we already did, but let me stress them once again because they're important. If I have a defining lattice, then this will be stable, just by definition of the Pleskens-Sassenhaus ring. If I take any two intersections or sums of defining elements, these will be also PZ stable. And scalar multiples by the uniformizer will also be stable. So the Pleskens-Sassenhaus ring is defined also up to equivalence classes, choices of equivalence classes. And here's a proposition that tells us that if gamma consists of diagonal lattices, which means, if you remember, of the form LU, all with respect to the same basis, then PZ gamma is graduated. Namely, it can be defined as lambda m for a matrix M. And the converse is also true. So if I start with the graduated order, then the defining lattices will all have compatible bases. Are there questions so far?
When you say graduated, can you just, do you mean graded, or is this?
No, it's, sorry, let me go back 1 second to the slide where I defined it.
Oh, so maybe I just missed it, sorry about that.
Yeah, no problem at all. So here we said that any order of the form lambda m is called graduated.
Oh,
so this is the definition, okay. Right? But yeah, it's maybe not the best name. We just decided to follow the literature, but yes.
Yeah, thanks for going back.
No problem. So yeah, I got to this slide, which is the moment where I would, in some sense, go back to what I told you and tell you how we can see this from the point of view of tropical operations, unless there are any questions before I continue. All right, then I guess I will just continue. So here's my next slide, and this is, I imagine you're all very familiar with these operations. I just wanted to set the notation and give a little first example. So min plus and max plus algebras, we define starting from these operations, and we really look at both min and max at the same time in this project. So the bar underscore bar is the min plus, upper bar is the max plus, and then the dot is the usual dot, which is just a sum. And we see already why, in terms of lattices, this is a convenient notation, because if we take any two diagonal lattices and we intersect them, well, we get again a diagonal lattices that corresponds to the max sum of the vectors. While on the other side, if we take a sum of two diagonal lattices, then we get again a diagonal lattice that corresponds to the min sum of the two vectors. So you see that already this is very useful, because we saw if we have stable lattices, we can add them and intersect them, and this is what these operations do for us also. And these operations, we can also extend them to operations with matrices. So we just do the usual multiplication. We proceed as we would multiply normally matrices, but we just now replace with these new operations. I don't know if I should spend more time here. I guess you're all familiar with this, with these operations. So I'll just continue, and if someone wants me to go back, just please speak up. Here is our first step into approaching what I told you before in terms of tropical geometry. So we define a polytrope from a matrix M to be the collection of all vectors in R to the D modulo R1 that satisfy this inequality. And we follow Josvik, Kulas, and Tran with calling them a polytrope, but yeah, in the literature, this can also be called an alcove polytrope. Why is this important for us? Well, first of all, with these new operations, we can write any order. So a module lambda m, we now know when it's an order. This happens if and only if the matrix we started with is min tropically idempotent. So this is a very compact way of giving the condition for this module to be a ring. Also, if a diagonal lattice is stable, this we can check by just checking this inequality. Again, by checking min products and comparing what we get. Moreover, what these polytropes do for us, well, they're integral points. They characterize the lambda stable lattices. So what do I mean by this? I mean that there's a one-to-one correspondence between the equivalence classes of lambda stable lattices and integral points in the polytrope. And here is another theorem. We saw before that if we had a graduated order, all the lattices, if we had diagonal lattices, these will define a graduated order in terms of the Pleskens-Assenhaus ring. And I told you the other way around. Here's the way you do it. So this is a very constructive thing. So if you start with diagonal lattices defined by U1 up to UN, then your Pleskens-Assenhaus ring will be equal to lambda m, where m is defined by this sum. And let me just remind you that m of u was just defined as to have entries ui minus uj. Good. And of course, from a collection of lattices, you can define the ring, the Pleskens-Assenhaus ring, and then compute the stable ones, but also you can recover, of course, the ring from the stable ones by just taking the Pleskens-Assenhaus ring. So this is a way of going back and forth. So if we go back to our example, what can we say? So first I showed this to you a bit quickly, and this is an example that I will be dragging with me throughout the talk. So if at some point you get sick of seeing the same example, please let me know. So what do we do here? We take as defining vectors -2, 1, 0, 2, 1, 0, and -1, 3, 0. So these three red vectors. And from these vectors, we get three lattices. And from these three lattices, we define a Pleskens-Assenhaus ring that is defined by this matrix. So let me just quickly, you can see it here, right? If you have the lattices LU1, LUN, you take the Pleskens-Assenhaus ring, which was just the intersection of their endomorphism rings. And this will be equal to lambda m, where the m is defined like this, exactly like this. And you will get back the matrix I showed you at the beginning. interestingly enough, this QM is the max plus triangle that is defined by these three vertices. And you could, if you stare at this picture long enough, you could also observe that you could get, instead of taking these three vertices here, you could take these other vertices and instead take the min convex hull. So in general, at least for this example, you see that this guy is min and max closed. And right. And another thing you can see is that, for example, let's notice it here immediately, but I'll get back to this. If you allow multiplying, adding some multiple of the all one vector, here, if you add 2, 2, 2, you get exactly this first column. Here, if you add, well, this is just the third column. Here, if you add 1, 1, 1, you get the second column. So you see that there is a way, somehow, to relate the vertices, in this case, the min vertices, min plus vertices, to the matrix. We'll see also that there is a way of relating the max plus vertices to the matrix. And I'll get back to this picture again, and then I'll give you some more insight on at least this picture. But I hope that this is clear, at least a bit more, now how this classifies the equivalence classes of the stable lattices. And another thing we can do is, so now we know that polytropes are important for understanding these stable lattices. We can also ask how many of these polytropes there are. So following Tran, we define the polytrope region to be the collection of matrices with zeros on the diagonal, their min plus idempotent. And then we also define the truncated polytrope region to be the collection of those matrices from PD that are at most m. Remember, these have real coefficients, so we're all good. And what we do in our work, we also study these objects. So because of these idempotent conditions here, we know that PD is a d squared minus d dimensional convex polyhedral cone. We also managed to compute the number of facets of PD, which is d times d minus 1, d minus 2. And for small numbers here, we compute the f vectors and the vertices of PD. And I will show you where you can find the code that does this at the end of my talk. And as I mentioned before, these are sort of objects that we use to count and to count the polytropes. So for example, if we look at the truncated polytrope region, this parameterizes all the subpolytropes of QM. If you want to see this from the point of view of the rings, well, this parameterizes the orders that contain lambda m. And this just follows from this inequality here. Okay. And now there are some matrices that are somehow nicer to deal with because they really allow us to say a lot about the structure of modules and of the whatever the polytrope parameterizes. And these are just the matrices that satisfy Mij plus Mji, and we call them in standard form. What can we say when we have such a matrix? We can say also a lot about the stable lattices. So for example, we know that if we take M in standard form and QM is the polytrope that we define from it, then this is both a min plus and a max plus simplex, but also the min plus vertices, they correspond to the columns of M and they represent the projective modules. On the other hand, if we go with the max plus vertices. These are minus the rows. These are represented by minus the rows of the matrix, and they represent the injective modules. So this also tells us exactly, for example, that we always have d isomorphism types of injective modules and d isomorphism types of projective modules, which is actually pretty nice. And right, and this could be seen, for example, also as a corollary of a result of Kulas and Josvik, where they say that every polytrope in dimension d-1 is the convex hull of d points. And these d points are exactly, depending on what you take, min or max, either the injectives or the projectives. This is also very nice. Okay, so back to this picture. You can now see that, well, I don't have the defining elements of the UIs anymore, but these are exactly the same as taking minus the rows. What else can we see from this picture is that I told you that you can, once you have two stable lattices, you can add them and intersect them, and then you will find other stable lattices. Each cell that you see, so here we have 3 cells, they parameterize the modules that come between the sum and the intersection of these two modules. So if you look at this picture, you also see even more than you would expect. So you exactly know that whatever comes in the cell are these modules, the stable modules that come between the sum and the intersection of these guys. I wonder whether there was something else I wanted to say about this picture. Right. And of course, here, all the vertices are busy with being either min plus or max plus vertices. This, of course, does not need to be the case. So here's another example where I already changed the color code. So earlier we had the red ones were the max plus and the blue ones were the min plus, and now I switched the things around. But this is an example of a tropical ball in dimension 3. And this is defined as a polytrope from a matrix, a 4x4 matrix that has zeros on the diagonal and ones all outside. And we see here that the blue vertices are the max plus vertices, while the red ones are the min plus vertices. And the yellows, well, these are just other vertices, but that we don't need to define our polytrope as a convex hull. Okay, are there any questions so far? All right, then I want to say, tell you something more about other connections that we can make. We looked at modules of the associated to the ring, but of course, we can think of ideals and fractional ideals as well. And what are these? Well, the ideals of lambda m are just parametrized by, you define them in the same way sort of as the lambda m, but you ask for your defining matrix to satisfy this condition. So it's really a bit like an ideal. You ask that left multiplication and right multiplication preserves your object, and we collect all these matrices that do this in a set that we call QM, which is the ideal. We refer to it as the ideal class polytrope. And matrices in there satisfy different properties. So for example, if you take an integral matrix with zeros on the diagonal, then these are just the matrices that define the orders. If you take any two matrices and you multiply these two ideals, well, you get an ideal that is defined by the min product of these ideals. And if you look at QM with the min product, this has the structure of a semi-group where the neutral element is M. And now you can ask, is this a group always? Well, it is not, but it will contain a biggest subgroup in there. This group we denote as GM, and we call it the ideal class group. So in some sense, this is trying to mimic what happens in number theory, though it is not quite. You see, this is not automatically taking the fractional ideals, that does not automatically give a group. So we have to sort of take the biggest group in there. And what we do, we compute the isomorphism types of these groups for small j's. And remember, the j's were these matrices with the zeros on the diagonal and the ones outside. But we do not know, higher than dimension 4, how the sequence continues. We also understand very little about the algebra of these groups. So we're very happy to get any input on this if you see what could be said. Another thing that I wanted to mention, and this is sort of how we want to continue, so thinking of this project at a different level, is that all of this we understand from the point of view of buildings. So let me tell you what a building is in the context we are in. So this is a simplicial complex where the vertices are given by lattices and actually equivalence classes of lattices. So anything that is scaling, we allow and we put all in the same class, and this will be one vertex. And a simplex will be given by a collection of lattices that satisfy up to permutations and choice of representatives, inclusions like this. And what we saw today is, from the point of view of buildings, this all happens in one apartment. So you remember we always spoke about diagonal lattices, about compatible, they have compatible bases. So essentially, from the point of view of buildings, this means that we're working in one apartment. But a building is actually a gluing of lots of apartments. So we are somehow restricting ourselves to a small part of the building. And in terms of the building, what we do is that when we look at these Pleskin-Sassenhaus strings and we get these graduated orders, well, the polytrope, which describes the stable lattices, this can be also seen as the geodesic convex hull of the defining lattices. So we have a very good understanding of how to start with vertices of the building and get everything that is stable from just those. We just need to take the geodesic convex hull in there. The big question is, however, once you're not stuck in your apartment, how does life continue? And this is what this project wants to do. So we want to leave the apartment and we want to be able to say what happens for bigger rings. And we have done quite some work in that direction. We considered particular new sort of convex objects in the buildings, for which we understand this connection between QM and lambda M. Sort of we lift it and we look at balls and at Minkowski sums of balls together with polytropes. And these we call polytropes. So this is another paper which we finished recently. But yeah, what happens after that, we don't know, and we're very excited to know. Anyway, I want to thank you for now for your attention, and also tell you that everything I told you today, you can also check out again on our math repo page. And maybe, let me see if I'll open it here and show it to you. This is a repository that was started by Maza and you in 2017, I believe. I'll get to the main page of this in a second, but I wanted to show you, this is our page where we sort of like summarize a bit what we do. And at the end here, if you click, now I have to remember where it is. Oh, here's the notebook. Then you will find the code that was used, for example, to compute the polytrope regions, so the facets, the vertices, etc., but also to compute the isomorphism types of the ideal class groups. So if you found it interesting, if you want to try yourself, here you can find a starting point. And as I mentioned, this is a bigger, so of course we posted our work here, but on this repository that is hosted by the Max Planck Institute in Leipzig, you can find the work of, well, different people associated to the Institute. And yeah, I just wanted to say that this was started, yeah, exactly, in 2017 from Yuren and Maza Sayar and Amin, but now there's different people that are sort of like keeping it going. So I guess this is everything I wanted to say. And yeah, I'm happy to get questions. Thank you.